Yeah. Okay, thank you. And can everybody hear me? Okay. So I'm going to be presenting the paper Learning Combinatorial Functions from Pairwise Comparisons, which is joint work with Nina Balcan and Colin White. So as the title suggests, our goal in this paper is to be able to learn a function up to pairwise comparisons from pairwise comparisons. And in this paper, we provide a general algorithmic framework, which we then instantiate for a wide array of combinatorial function classes. And to motivate this work, I'm going to start by just recalling what do I mean by a combinatorial function, and then I'll recall a particular example of a subclass of combinatorial functions that we would especially like to learn up to pairwise comparisons, which is submodular functions. So a combinatorial function is simply one that maps subsets of some ground set of n elements to the real line. So for example, the influence of subgroups in a social network is a combinatorial function. And one subclass of combinatorial functions that is ubiquitous in machine learning, computer science, and many other scientific fields are submodular functions. They're generally regarded as the discrete analog of convex functions, and they're especially prevalent in microeconomics because they model consumer diminishing marginal utility. So suppose I'm a consumer with a submodular function in my head as my valuation function for some set of n elements. It might be easier for me to tell you which of two subsets I like better than to assign a particular value for a subset of goods. So this motivates why we might want to learn submodular functions up to pairwise comparisons. So just to pin down the model here, we assume that there's a distribution on the set of all subsets over this ground set V, which is of size n. The learner receives samples from this distribution, and then it has access to a pairwise comparison oracle. And the oracle takes as input two subsets and returns the one that it likes better, as according to this underlying function f. And then we say, just informally, that f is comparator learnable if the learner, after interacting with the oracle for some fixed number of steps, if the learner outputs this hypothesis function g, such that with high probability on two random subsets, s and s prime, drawn from the distribution, it's unlikely that the value of the first set is less than the value of the second set, yet g incorrectly predicts otherwise. So the formal definition is a mouthful, so you can find it in the paper. And we show that for many of the subclasses we care about, such as submodular functions, it's NP hard to learn to this level of precision. So to weaken this definition, we say that f is comparator learnable with separation alpha if the comparison hypothesis g that the learner returns with high probability for two subsets, s and s prime, drawn for the distribution, it's unlikely that their value is a multiplicative factor of alpha apart, yet g predicts incorrectly. Okay, and now I'll just state our most general algorithmic result, and then I'll give a brief overview of the algorithm itself. So suppose that we have this function class f, and every function in the class can be approximated to a multiplicative factor of alpha by the pth power of a linear function. So what I mean is that there exists these two values, p and alpha, such that for all functions in our class, there exists a w vector, a weight vector, such that this inequality holds. Okay, for example, we know that submodular functions can be approximated to a square root of n factor by the square root of a linear function. Then we prove that if such a p and an alpha exist, then f is compared or learnable with separation alpha. So here again is just the informal definition of what that means. Okay, now some very brief intuition for the algorithm. Now suppose that such a p and an alpha exist for our function class f. That it's not hard to show that if I have two subsets s and s prime that are separated by a multiplicative factor of alpha, then if I take the corresponding weight vector w from here, if I take that weight vector and dot it with chi of s is the characteristic vector of s, then that value is going to be at most that weight vector dotted with chi of s prime. So in other words, this means that there exists a linear separator classifying sets as less than f of s and greater than f of s prime. So suppose hypothetically that I had two sets in hand, s and s prime, that I knew had value alpha apart, like in this picture. Then I could learn the linear separator that correctly classifies the pairs which are either less than f of s and greater than f of s prime. So pairs that span the values f of s and f of s prime. Okay, this isn't going to work as an algorithm, of course, because for one, I can't know for any two sets s and s prime whether they're an alpha factor apart. And moreover, it would only allow me to classify a very small subset of the pairs I care about, namely those that span f of s and f of s prime. But I can still use this lemma and this intuition for the full algorithm, which goes essentially as follows. I draw two samples, and I use the first sample to discretize the range into what we call landmarks. And then for each landmark pair, I attempt to learn a linear separator that classifies sets which span that landmark pair. I know from my lemma that if for these two landmarks, s sub I and s sub j, if they're an alpha factor apart, then indeed I can learn this linear separator. All that remains is on an input pair s and s prime, I search for a linear separator that classifies s differently from s prime. Okay, and so these are just a few of our results. We instantiate that general algorithmic framework from the previous slide for many different classes of combinatorial functions. And we get both upper and lower bounds on the level of separation needed for learnability. And just to summarize, I presented a general algorithmic framework for learning combinatorial functions up to pairwise comparisons from pairwise comparisons, and we provide tight and almost tight bounds on the level of separation necessary for learnability. And we emphasize that the amount of separation necessary is very strongly related to the amount of structure that the combinatorial function classes exhibit. And so one interesting future direction would be to see if we can tighten this submodular upper and lower bound, if we can make them match. So thank you.